Hello everyone, my name is Bruno Garcia and I'm honored to present my capstone project titled Improving Path Planning Algorithms for Autonomous Drones in Complex Urban Environments. This project is the culmination of my academic journey in information technology sciences at the University of the Cumberland, where my emphasis has been in artificial intelligence. Today, I'll walk you through the research I conducted, the insights I discovered, and the future possibilities for autonomous drone systems in the urban settings. Project overview. Autonomous drones are rapidly becoming part of our everyday reality. From package delivery and traffic monitoring to search and rescue missions, these systems offer incredible advantages in both convenience and efficiency. However, their use in complex urban environments where tall buildings, pedestrians, and dynamic conditions are common poses unique challenges. This project seeks to explore how artificial intelligence, particularly reinforcement learning, can be applied to drone path planning to improve their adaptability and performance in unpredictable real-world settings. Statement. At the heart of this challenge is a path planning problem. Traditional algorithms like A-star and Dijkstra are excellent at plotting efficient routes in known static environments. However, they falter when things change mid-flight, like a moving car, sudden construction, or shifting wind patterns. On the other hand, AI-based methods, especially reinforcement learning, can dynamically adapt to change but require extensive training, data, and computer power. The question my research tackled was, how can we combine the strength of both approaches to create a path planning strategy that is efficient, reliable, and adaptive to real-time changes and objectives? To address this problem, I defined 6 key goals. 1. Conduct a comprehensive review of current path planning algorithms used in drone navigation. 2. Explore how these methods can be adapted for 3D urban environments. 3. Analyze the role of real-time sensor data, like GPS, LiDAR, and cameras, in navigation. 4. Investigate how reinforcement learning enhances adaptability. 5. Simulate the performance of different techniques based on existing case studies. And 6. Identify real-world use cases and make practical recommendations. Practical navigation methods. My literature review began with traditional algorithms. A-star and RRT, rapidly exploring random trees, are deterministic methods that work well in structured environments with predictable obstacles. A-star guarantees the shortest path and is fast in open environments, while RRT is better at navigating complex, cluttered spaces. However, both approaches require prior knowledge of the environment and have limited ability to adapt on the fly, especially in dynamic urban settings. AI and hybrid navigation methods. Well, this led me to the AI-based solutions, reinforcement learning models like deep Q networks, DQN, and proximal policy optimization, PPO, have shown incredible potential for real-time navigation. These models learn through trial and error and in simulations and can generalize their learning to similar environments. However, they require intensive training and powerful hardware, which limits their feasibility in smaller, resource-constrained drone systems. That's where hybrid models come into play. By combining the structure of algorithms like RRT with the adaptability of reinforcement learning, hybrid models can improve both reliability and flexibility. These models adapt to changes while keeping computational demands within reason. Fusion and multi-agent systems. Another major theme in my research was sensor fusion. In an urban setting, drones need to combine data for LiDAR, GPS, IMUs, and cameras to build an accurate model of their environment. Each sensor has its strength and limitations. GPAs may lose signal, and cameras struggle in poor lighting, but together they provide redundancy and robustness. Additionally, I explored multi-agent systems, where multiple drones collaborate and share information. This is especially useful for urban surveillance, coordinated deliveries, or search and rescue operations, allowing drones to avoid collisions and optimize shared airspace. Research methodology. To conduct this project, I used a design-based research (DBR) methodology with a quantitative focus. This approach was ideal because it allows for iterative testing, refinement, and adaptation. While I didn't have access to run live simulations or train reinforcement learning models due to technical constraints, I extensively reviewed peer-reviewed case studies, academic research, and simulation-based findings. I also evaluated comparative data from simulated environments like AirSim and Gazebo, both of which are commonly used in real-world robotics research. Process. My research followed four main phases: selection of algorithms, identifying core path planning approaches, both classical and AI-based. Then, simulation environment review, analyzing results from platforms like AirSim to evaluate performance in realistic 3D environments. Then, performance comparison, focusing on metrics such as obstacle avoidance, energy consumption, computation time, and adaptability. And finally, model refinement, using this data to propose a hybrid path planning model that meets both technical and practical requirements. Then performance findings. Here's what I found. A-star is excellent in static, well-mapped settings. DRL models perform better in dynamic, unpredictable environments, adjusting routes on the fly. Hybrid models, especially those integrating RRT with reinforcement learning, show the best overall results, achieving efficiency, adaptability, and lower computational costs. And finally, sensor fusion enhances accuracy with latency trade-offs. Fusion and real-world constraints. Sensor fusion significantly enhances drone perception and path accuracy. However, challenges still remain, like latency from processing multiple data streams, signal interruptions, and environmental conditions like fog or wind. Interestingly, reinforcement learning models were shown to adapt to these real-world challenges better than classical algorithms, although at the cost of requiring more advanced onboard processing. Applications and implications. The implications of this research are broad. Urban logistics. Drones that can dynamically reroute around construction, pedestrians, or no-fly zones. Search and rescue. Navigation in collapsed buildings or disaster zones without relying on GPS. Traffic monitoring. Coordinated drone swarms tracking congestion or incidents in real time. These are just few examples of where smarter AI-enhanced drones could have a real impact. Future directions. There are three key directions this research points toward. Neuromorphic computing, which mimics how the brain processes data and could dramatically reduce power consumption while increasing real-time responsiveness. Transfer learning would allow training AI models to quickly adapt to new environments without starting from scratch. Decentralized multi-drone coordination, where drones communicate with each other rather than relying on a central server, will be vital for scaling operations safely. Encountered. Of course, no project is without its challenges. I was unable to directly train reinforcement learning models due to computational constraints, which limited hands-on experimentations. Synthesizing AI theory with classical models was also complex, especially when evaluating which combination would be the most realistic for near-term adoption. However, these limitations encourage deeper research into hybrid approaches and alternative design strategies. Takeaways. In closing, this project reinforced my belief that the future of autonomous drones lies in hybrid systems, blending classical algorithms with adaptable AI models. Sensor fusion, real-time adaptability, and efficient decision-making will be key to safe, scalable urban drone navigation. About the possibilities this research opens up, I'm grateful for the opportunity to share it. Thank you so much for your time, and I look forward to any questions or feedback.